In most physics books, you'll find a table giving moments of inertia for the types of objects that we often encounter in this chapter. I've drawn 5 of those objects here and listed their moments of inertia. What I want to do in this talk is show you how to integrate the moment of inertia, that's this MOI here, expression that I gave you last time. The moment of inertia for an extended object is the integral of r squared dm. Before we jump into that though, let me point out a few things on these diagrams so we know what we're looking at. First, each of the objects has a mass m. So in all of these moment of inertia expressions that I've written down, the m's are the mass of the object. This rod or stick right here has a length of capital L, so this L right here is its length. And each of these round kind of objects has a radius of r. So the solid disk and the hoop or the ring and these 2 spheres all have a radius of r. The last thing to point out about these figures is the axis of rotation. Before you can calculate a moment of inertia, you have to know what axis the object is rotating around. I've indicated those in orange. So for instance, this rod or stick has an axis through the end here. So imagine an axis coming towards you so that the rod or stick is going to rotate this way about that end. That's this moment of inertia here. If we move the axis to the center, where the center of mass is located, it would now rotate this way, and that gives us this moment of inertia. The solid disk has an axis indicated in the same way. Here's the axis here, so that the disk is going to rotate around in the plane of the screen. Same thing for the hoop or ring. For these 2 solid spheres, the axis of rotation goes through the center of mass, and it spins this way. So for this hollow sphere here, think of a basketball spinning about an axis that goes through its center. There's one last thing I would like to point out and have you notice before we jump into evaluating these integrals. For all of these round-shaped objects, the 4 of them over here, notice that each of their moments of inertia go as some coefficient times mr squared. Some coefficient, it's 1 in this case, times mr squared. A coefficient times mr squared. A coefficient times mr squared. They all have the same form. The only difference is what that coefficient is out in front. It'll turn out that that coefficient falls out of the integration. When we perform the integrals, that's going to be where this coefficient shows up. And what it tells you physically is how the mass is distributed relative to the axis of rotation. As the object's mass gets farther from the axis, that coefficient gets bigger. The moment of inertia gets larger. Remember that the moment of inertia gets larger when you have mass that's located farther from the axis. So in a case like this solid disk, where you have mass close to the axis, medium distance from the axis, and far from the axis, you'll have a smaller coefficient than over here, where all of the mass is far from the axis. And the same thing applies down here. In the solid sphere, in 3 dimensions now, some of the mass is close to the axis, medium distance, and far away. That'll give you a smaller coefficient, a smaller moment of inertia than this hollow sphere where all the mass is in a shell, the same radius r away from the center. So let's jump in and start evaluating these integrals. I'll do them in this order. First we'll do the rod or the stick, and then we'll jump into all the round ones. We'll do the hoop or the ring, followed by the solid disk. Then we'll do the hollow sphere, and we'll do the solid sphere last. Just to give you a bit of notice about what's coming, the rod or the stick is a pretty easy one to evaluate. The hoop or the ring is pretty easy. The solid disk is not too difficult. The hollow sphere is medium difficulty, and the solid sphere is kind of a difficult one. We'll save that one for last. It's certainly the most challenging of the bunch. All right, let's jump in and do the rod or stick first. So here is the rod or the stick. We'll say that it has a mass of m and a length of L. I've added a coordinate system here, calling this the x-axis and letting this be x equals 0, where the pivot or the axis is. So we're going to calculate the moment of inertia I of this rod or stick about its end, so that as it's pivoting, it's going to be moving in the plane of the screen this way. And my integral tells me to add up the distance squared of each mass from the axis. So that's what we need to make this integral do. Add up each little piece of mass in this rod or stick times the distance squared from that mass to the axis. Let's draw an arbitrary piece of mass, and we'll call it dm. Imagine I take this little tiny piece of the rod or the stick, and I say it has mass dm. What I need to do now is imagine sliding this piece from here all the way over here so that I account for all the mass in the rod, adding up every time the mass times the distance from the axis squared. Now that distance in this case is right here. So r equals the x value of our little piece of mass. The way to set up this integral is to change variables so that we're integrating over space, so that we're integrating over x, the length of the rod, instead of integrating over the mass. And we do that using a density. The mass density of this rod we'll call lambda. That's typically what we call one-dimensional densities, and it equals the mass per unit length. If the density is uniform, it's the same everywhere along the rod, the density is just the total mass divided by the total length. And then I can say that dm, the amount of mass in this little chunk right here, is the mass per unit length times the length. And now I have said that the width of this little guy here is dx. So I can rewrite my integral as x squared, because r equals x, times dm, which is lambda dx. And we integrate from 0, from here, all the way out to the end of the rod, capital L. The density lambda is constant, so we can drag it out of the integral, and we get this, which is an easy integral to do. We get lambda L cubed over 3. Lambda, the density is the rod's mass divided by its length, times L cubed over 3, which is where we get our result. The moment of inertia for the rod about its end is 1/3 its mass times its length squared. All right, now let's also find the moment of inertia of this rod about its center, about the center of mass. I'll move this result up here, and now we want to move the axis from here to the center and put it right here, so that if this end goes this way, this end's going to go up that way, like a propeller. And we want to know the moment of inertia now about the center of mass. There are two ways to do this. We could set up another integral and do it that way, or we could use the parallel axis theorem. Let's do it that second way. The parallel axis theorem tells me that the moment of inertia about any axis, we'll pick the end because we already know it, equals the moment of inertia about the center of mass plus the total mass times the square of the distance that the axis has moved parallel to itself. So in this case, the axis was here, coming out of the screen toward us, and now we've scooted it over here, a distance d equal to L over 2, half the rod's length, to get it to the center. So we can solve for the moment of inertia of the center of mass and substitute in our known results. We get I and minus md squared, and d is half the rod's length. So we get 1/3 ml squared minus 1/4 from this 1/2 squared. And 1/3 minus 1/4 equals 1/12. So the moment of inertia of the rod about its center of mass is 1/12 ml squared. All right, let's look next at the hoop or the ring. I've drawn here a hoop, so we can think of this as being like a hula hoop where all the mass is concentrated out here, and we're going to calculate the moment of inertia about an axis through the center. So we can imagine the hoop rotating this way in the plane of the screen. And we need to find its moment of inertia equal to r squared dm. So again, what we need to do is add up every piece of mass times the square of the distance from the axis to that mass. Let's pick an arbitrary piece of mass and see what we have. This little chunk of the hoop right here, I can call dm. We can notice that it's a distance r away from the axis. And in fact, every little piece of this hoop is the same distance r away. So if I imagine adding up all of the little pieces, moving around this hoop as we go, every single one of them is going to be a distance capital R away. So this little r here is actually a constant, and it equals the hoop's radius. I can drag it out of the integral, and I get r squared dm from 0 to the total mass. So we imagine now just going around adding up all of these little dm's until we get all of the mass of the hoop. And that just gives me m r squared. So that's one way of doing this one. I want to show you another way because it will set us up and get us some practice for something that will be useful next time. So here's another way to set up and solve this integral. Moment of inertia of the hoop is integral of r squared dm. And like last time, we have this little element of mass dm. I want to rewrite that using the density. This is a one-dimensional distribution of mass. It's all along this circular arc here. So the density is the mass per unit length. If the density is uniform, which we'll assume it is, it's the total mass divided by the circumference, 2 pi capital R. And now I can write dm, this little chunk of mass, as the density, the mass per unit length, times the length of this little thing here. So this little thing, we'll say, has a length ds. And we can write ds using the arc length formula. If we call this direction the phi direction, then this angle right here we could call d phi. It's a tiny little angle, and ds, this length, would be r times d phi. So my integral becomes capital R squared. Every piece of the mass is still the distance capital R away, the hoop's radius, times dm. And dm is lambda times ds. ds is r d phi. I'm going to integrate from 0 to 2 pi, meaning I'm going to go all the way around this hoop, picking up every piece of mass. So we get r cubed lambda integral of d phi from 0 to 2 pi, which just gives us a factor of 2 pi. So we get 2 pi r cubed lambda. Now lambda is the density, mass per unit length. So we can substitute that in. 2 pi r cubed, total mass, divided by length, which is the circumference. And a bunch of stuff cancels. 2 pi and 2 pi. This r turns it into r squared. And again, we have mr squared. So the moment of inertia of the hoop is mr squared again. All right. Let's look next at the solid disk, the hockey puck kind of shapes. All right, so here's our solid disk. It has a mass, capital M, and a radius, r. It's going to rotate around this axis so that it rotates in the plane of the screen, and we need to calculate the moment of inertia for this solid disk, equal to the integral of r squared dm. Let me just remind you that what we should get in the end is 1/2 mr squared. It's less than what we got for the hoop because some of the mass is closer to the axis, so we get a smaller moment of inertia. Alright, like before, what we need to do is pick out an arbitrary piece of mass that we can call dm. I'll pick that little piece right there, and we'll say that is dm. And now I need to imagine adding up that mass times the square of the distance from the axis as I cover this whole area. So here's how I want to set the integral up. I want to imagine that this dm is moved right here, and to add up every piece of it, I'm going to imagine rotating around in phi by 2 pi, and then expanding out in r, and just rotating around in 2 pi, going out in r, until the r gets all the way out to the radius of this wheel. So I'm adding up every piece of mass times the distance squared every step along the way until I've covered the whole thing. That's what the integral tells me to do. Let me erase that bit of mess right there. To set up the integral and do that, the first thing I'm going to write down is the density. Because this is a two-dimensional object, we call the density sigma. So the mass per unit area is sigma. If the density is uniform, the same all through this object, which I'll assume it is, the density is the total mass divided by the area, which is pi r squared. And now I can write dm, the little mass here, as sigma, the mass per unit area, times the area of this little red rectangle. Now that little red rectangle has two dimensions. There's a length and there's a width. Let's call this the width right here. And that distance is dr. If we're moving away in the radial direction, it has an extent this way of dr. The other side of this rectangle, this guy right here, has a length of r d phi, just like last time. If I imagine drawing an arc here, so that this is some little angle d phi, then this side of the rectangle has a length r d phi. So the area of that little rectangle, dA, is its length times its width, which I can write as r d phi dr. So let's go up here and substitute that in. R squared times dm, which I'm going to write as sigma times dA, r d phi dr. But now I have to integrate over two dimensions. I'm integrating over phi as I sweep around this way, and also over r. After going around in phi, I take a step out, I go around again, I go out in r, I go around again, I take a step out, and I go around, and I cover the whole thing. So the phi variable is going to go from 0 to 2 pi. The r variable is going to go from 0, where the axis is, to capital R, all the way out to the edge of the disk. Sigma is a constant. I can combine those r's, so I get sigma r cubed d phi dr. Phi from 0 to 2 pi, r from 0 to capital R. The phi integral is easy. The integral of d phi from 0 to 2 pi is just 2 pi. So I get 2 pi sigma integral r cubed dr from 0 to capital R. And that, of course, gives me 2 pi sigma r to the 4th over 4. When I substitute in the expression for the density, mass over area, I get 2 pi density, mass over pi r squared, times r to the 4th over 4. And now a bunch of stuff is going to cancel. That r squared turns this into an r squared. That 2 turns that 4 into a 2. And the pi's cancel, and we can see that what we're left with is mr squared over 2. So this equals 1/2 mr squared. The moment of inertia of a solid disk rotated about its center of mass in the plane of the screen. Now we're going to move to the three-dimensional shapes, and we'll look at the hollow sphere next. Here's our spherical shell, our hollow sphere, and we want to find its moment of inertia by solving this integral. I'll remind you from what we had before that the answer we'll get in the end, the moment of inertia of a hollow sphere, is 2/3 mr squared. So here's our sphere. I've drawn it as large as possible to help us with one of the challenges that we'll face here, and that's the fact that we're going to have to work in 3 dimensions. So that makes this one a bit more challenging than the last. And the particular challenge we're going to face is sorting out how to write dm in some coordinates that we can integrate over so that we can take the dm, I've drawn it here, so that we can take the dm and sweep it all over the surface of this sphere, performing this integration, adding up the mass times the distance squared at every step along the way. So the way we're going to do that is to imagine that we take this little patch here that I've shown, and we would rotate it around here, and then take a step down, rotate it around, take a step down, rotate it around, a step down, rotate it around, and we'll do that for all of the angles from straight at the very top, rotating it around and around and around, all the way down to the very bottom. That's our approach here. Now to get us started with that, let's define the density like we've been doing before. This is a 2-dimensional surface, the surface of this sphere. So the density is the mass per unit area. Assuming the density is uniform, that's the total mass divided by the surface area. 4 pi capital R squared, where capital R is the radius of the sphere. So that lets me write dm as sigma dA. This little piece of mass is the mass per unit area times the area of this little patch right here. Now I need to work out what dA is. To help us do that, let me draw a couple of reference lines. Let me first mark the center of this circle. As we sweep this patch around this way, it'll trace out a circular path, and this is the center of that circle. I want us to note the radius of that circle. That's going to be little r. Notice that little r can be expressed in terms of capital R, the radius of the sphere, and the polar angle to that patch. Let me draw the polar angle. If we go from the center to this point, and we call this the angle theta, that's the polar angle, then we see that little r is capital R times sine of theta. So our little r is radius of the sphere, sine of theta. And now I can imagine taking this line and sweeping it around the circular path up here through a direction that I'll call phi. So let's call this direction phi. If I take this line and sweep it this way, it'll trace out a path of length r times d phi. So that's one side of our little patch that we can model as a rectangle. The other side is this one right here. And that one has a length r times d theta. So this guy is capital R d theta, because this line of length L would sweep through some polar angle d theta to get to the other side. And that tells me what dA is. The area of this little rectangle is capital R, little r, d theta, d phi. And little r is capital R sine theta. So now I can rewrite this integral and solve it. It'll be in 2 dimensions. Little r is capital R sine theta, so we have that squared. And then I multiply that by dm, which is sigma times dA, where dA is the product of these two things. Little r, capital R, d phi, d theta. In my integration variables, then, for this one, go from 0 to 2 pi. I want to integrate all the way around each of these circles. And theta goes from 0 to pi. I want to integrate from the top of this around and around and around until theta gets all the way down here, and I'm integrating around the bottom. So that's the integral we need to do. Let's simplify it and see what we get. The phi integral is easy because there's no phi over here, so we just pick up a factor of 2 pi. So let's pull all the constants out and write that 2 pi. Here are 1, 2, 3, 4 r's. So we have r to the 4th sigma times the 2 pi from integrating over phi. And then we have the integral of sine cubed theta d theta from 0 to pi. Now that integral you can work out or look up however you choose to solve it. Either way, what you'll find is that it equals 1/3 cosine cubed of theta minus cosine of theta, evaluated between 0 and pi. And that, when you put the numbers in, equals 4/3. Okay, so this whole business here, this integral, just works out to 4/3. Let's simplify the answer then. I'm going to erase this bottom part that we don't need, so we have room to write. The moment of inertia for the hollow sphere is r to the 4th times sigma, which is the mass, over 4 pi r squared, mass per area, times 2 pi, times that whole integral, which works out to just 4/3. Now let's see what we have. The 2 pi and the 4 pi cancel to leave us with a half. The r to the 4th over r squared cancel to leave us with r squared. And this 2 and that 4 cancel to leave us with a 2/3 here. So let's look at what remains. 2/3 m r squared. And that's our moment of inertia. The moment of inertia of a hollow sphere, rotated about a line through its center, equals 2/3 m r squared. So that's good. We have one more, the solid sphere. It's the most difficult. It is similar to this one, but it adds an extra dimension because there's mass distributed throughout the sphere itself. So we'll look at that one next. So here's our solid sphere, like a Nerf ball or a bowling ball or whatever. It has mass m and radius capital R. And we need to find its moment of inertia by evaluating this integral, r squared dm. As before, I've identified a little chunk of mass that we'll call dm. And the idea is to calculate this integral by sweeping this little piece of mass through the whole volume occupied by this sphere. Because there's mass inside the sphere and on the surface, it's solid, we have to let this little piece of mass go everywhere inside here. So that's what our integral is going to do for us. Imagine taking this little piece of mass, starting it right here, and sweeping it in circles through everywhere. We're going to go out to the end here, all the way around, and then all the way down like we did last time. A difference here is that because there's mass inside, I've identified a little volume containing mass. This is no longer an area, this is a volume. So the density that we need to identify, we're going to call rho to indicate that it's a volume density. The density of this, if we assume it's uniform, which we will, the same density throughout, is the mass divided by the total volume, 4/3 pi r cubed. And that lets me write the mass inside this little piece here as the density times the volume of that little piece. And now I just need to figure out what the volume of this is, set up my integral, and integrate it. So what is the volume of this little shape here? There are 3 dimensions we need to identify: length, width, and height. We'll multiply them together and we'll have it. So let's pick these off one at a time. I've identified this as the z-axis going straight up from the center through the pole. And I did that because I want to call the height of this little rectangle, these legs here, I want to call those dz, a little height in that direction. So those guys are dz. Now this leg right here, we can identify just like last time as r d phi. That leg right there is r d phi. And now I just need this side. So that is just dr. The volume of this little thing I've been drawing, dv, is the product of those things. dr, dz, r d phi. Now, I don't want this z in my final expression. I want to change that to theta because I eventually want to integrate over theta. So I can take this thing, start at the top, let theta go to pi over 2 and then to pi as I integrate over this whole sphere. So I want to change variables. I want to get rid of z in favor of theta. If this is the angle theta, we can see that z equals r cosine of theta, so that dz is minus r sine theta d theta. Now we can see that what we really want here is the magnitude of dz. I want the length of this side. I don't care that we're going up or down. I just want the magnitude of that. So dv, our differential volume, becomes dr, magnitude of dz, capital R sine theta d theta, little r d phi. All right, let's write the integral out then. Notice that we're going to have 3 things to integrate over: r, phi, and theta. And the way this integral is going to be set up is that we're going to start up here at the very top, move out in r, and for every step in r, integrate around, take a step in r, integrate around it. When we get to this maximum value of r, we take a step in theta, come down, and do it all again, take a step in theta, do it all again, and in this way we trace out every piece of mass inside this solid sphere. So the limits on our integral are going to look like this. The phi integral, the one going around this way, is going to go from 0 to 2 pi. The r integral, the one going out this way, is going to go from little r equals 0 to its maximum value, which depends on theta. It's going to go from 0 to capital R sine theta. And the theta integral goes from 0 to pi. Now what goes inside the integral here is r squared, and dm is the density times dv, this volume. Let me write it this way: capital R, lowercase r, sine theta, d phi, dr, d theta, so that these variables to integrate over match up with these limits here. Phi is going to go from 0 to 2 pi, all the way around. R goes from 0 to its maximum, and theta goes from 0 to pi. And so we pick up every piece inside this sphere. Let's solve this integral. There are two constants we can drag out, and we can do the phi integral, picking up a factor of 2 pi. So we get 2 pi from the phi integral, rho times capital R. And we're left with r cubed sine theta dr d theta. Little r goes from 0 to r sine of theta, and theta goes from 0 to pi. When I do the r integral, I'm going to get r to the 4th over 4 between these limits. So that's going to give me r to the 4th sine to the 4th theta over 4. Now let me take that over 4 and make this thing here pi over 2. So you see what's happening there. That became pi over 2 because we divided it by 4 from this integral. And now I'm down to this integral with the capital R to the 4 times the 1 I already had. Gives me r to the 5th sine to the 5th theta d theta. Sine to the 5th because I had 1 here, and I picked up 4 more from the upper limit of that r integral. This integral you can work out or look up. I'll tell you what you get. You find that it equals minus 1/5 cosine to the 5th theta plus 2/3 cosine to the 3rd theta minus cosine of theta, all evaluated between 0 and pi. And when you work that out, you see that it equals 16/15. Alright, so that's what that integral equals. Now let me erase some stuff. We'll get some room and finish this. I'll erase this down here. And see what we get. The moment of inertia of a solid sphere is pi over 2 times the density. That's the mass over the volume. I'm going to write that as 3m over 4 pi r cubed times r to the 5th times this whole business here, which just works out to 16 over 15. So let's see what we have. I have r to the 5th over r to the 3rd. Those cancel to give me r squared. I have a 3 over 15. Those cancel to give me 1 over 5. And I have a 16 over 8. Those cancel to give me a 2 in the numerator. So let's see what we get when we pull it all together. We have 2/5 mass times r squared. So we got it. Alright, there's the moment of inertia of our solid sphere. 2/5 mr squared. That's a challenging one. There are several other ways to do this. If you look them up on the web, you'll find some nice slick methods, but that's how you do it in the most straightforward way possible. I hope that was a help to you. We'll see you next time.